So the final speaker can't join us today, so prepared a pre-recorded talk which we're going to play, so there will be no questions at the end, I'm afraid. So.
Hello, I'd like to take this time today to talk about my experiences with solving some systems of ODEs in the SciML and Julia ecosystem for Alzheimer's disease modeling. And I'm going to focus on observations and recommendations, from a user's perspective. In Alzheimer's disease, the formation of amyloid plaques, which are aggregates of the peptide A-beta-42, are the initiating factor in Alzheimer's disease. And I don't have time to describe the biology there, but suffice it to say that the kinetics are important, and that using an isotope labeling strategy and sampling of CSF from the lumbar space every hour for 36 to 48 hours after a 9-hour labeling with isotope labeled amino acids is the approach that we took. It's a mass spec-based approach. The data that we get out is the ratio of labeled A-beta peptides to unlabeled A-beta peptides, and labeling period is shown in gray, and the labeling over time these peptides is shown. There's a pretty stark difference between people who have plaques versus people who don't have plaques in the aggregating peptide A-beta-42 in comparison with other forms of A-beta. So that's the nature of the data. The nature of the model is that there are enzyme kinetics. The peptides are produced, they're inside the brain. They can be transported across the blood-brain barrier. They can be exchanged into the cerebrospinal fluid, which then sort of eventually, via pulsatility within the CSF due to the heartbeat and respiration. The mass of labeled A-beta-42 eventually makes it down to the lumbar space where we can sample it. The A-beta peptides can be degraded within the brain, or they can form plaques. And using a simple compartmental model, linear time invariant, we were able to some interesting conclusions about the kinetics of A-beta-42, and showed that its clearance actually increased in Alzheimer's disease, and this probably represented active deposition. That's an interesting result. However, there's a piece of data that we couldn't fit to that steady state model, and that was the fact that as we sampled CSF over 48 hours, every hour withdrawing 6 mils, we found that the concentration of the A-beta peptides rose over the course of the experiment. 6 mils with a CSF being withdrawn every hour is a lot. Typical production rate is 23 mils per hour. So, we're definitely knocking the system out of steady state. So we need to account for that in our model. Looking at MRI data, we knew that when you withdraw CSF, that you need to make up some volume somewhere in the central nervous system, and where that is in the lumbar space. And so we had a compartmental model, still in essence, it's a compartmental model, but the volumes of one of the compartments is changing over time. It's changing in a relatively predictable way. Okay, so this is the nature of the model. This compartment's volume is changing. We have Michaelis-Menten kinetics. We have flow through of CSF from site of production to sites of absorption of CSF. But we also have these bidirectional flows that essentially, serve as a diffusion process, so that A-beta peptides can be transported down concentration gradient. So that's the nature of the model. Fairly simple, could be solved exactly, but probably at the cost of accuracy. Suffice it to say that the modeling approach allowed us to determine parameters and draw conclusions about the fate of A-beta peptides. And this work is published, and we have additional work that will be published in the upcoming months. So this concept of having a compartmental model where one of the compartment's volume changes is relevant to clearance or ejection of mass from the gallbladder, or I guess intermittent emptying of the gallbladder is what it would be called, as well as emptying of milk from an udder. And this shows one of the earliest papers that I can find on experimental models with variable volume compartments. And I put together a Mach-E interactive simulation that I hope people will look at and maybe use as a test example, because I compare the numerical solution to directly solving using matrix exponentiation and showing just how sensitive matrix exponentiation is to the setup of the equations themselves. And would love some feedback on this, particularly to see if there are ways to improve the direct solution, and just to ensure that there isn't a numerical precision issue that is specific to Julia. The route to determine these parameters it's nested. There's nested optimizations, and that's kind of where the complexity arises. Why are they nested? Well, we have our parameters that we want to determine, but we also have measured the concentration of A beta in CSF at time equals 0. And from that, if we assume that the system was at steady state at time equals 0, then we can use these measurements to determine 3 parameters in our models, because we have 3 peptides, and these are the parameters that I chose to determine. And I determined them using an optimization where I'm solving, the same ODEs. It's just that there's no introduction of label and there's no CSF withdrawal. Comparing the output of this at time equals 0, steady state, to measured values, I was able to determine these 3 parameters. And then the guesses of these parameters plus the determination of these 3 parameters, which of course depend on all of these parameters, then was fed back into the dynamic system of ODEs, where label was introduced and CSF was being withdrawn every hour. Optimization, right? Many solutions to these equations as part of the optimization. But eventually, we find values for these parameters where the output of the model it matches well the A beta labeling time course data. If you look at the code itself, there is some code on GitHub already, and next few months there will be the code that's shown here, which is an improvement for sure. You'll notice that it's set up in ways that make sense, from the SciML perspective, with ODE problems, optimization problems, steady state problems. But as you dig down, you start to see that something started to fail. So, for example, I'm using Nelder Mead here because the nested AD proved to be slow. I additionally had to, sort of strip away the optimization problem and interface with the optimized function itself directly. So, this is a bit of a failure, honestly, because it would be nice to have this be fully AD. Tricky though, very tricky to have this nested AD. I was able to do it with toy problems, but it got to be incredibly slow with this full problem. Modeling toolkit, I'm not sure that it would actually save time with this sort of nested problem. I would tend to say that it would probably slow things down. One thing with the nested problem is that, is going to require pointer-like sharing of values between functions, and this can be done with, arrays with enclosures, and this works. But, looking at the stack traces when trying to do AD, there does appear to be some code bloat associated with all of these closures that are involved. There was definitely need to check allocations and type instability. The guidelines for performance in Julia are very clear in the documentation. It's just that, the examples that are used throughout violate those rules. So it would be nice to put that kind of more upfront within SciML itself. There's some small things like data interpolations should perhaps return a value. Have the ability to say that at time equals infinity, like my function should have this value. And then when solving a steady state problem, it would be nice to be able to say, oh, like I'm going to deliver to the function that contains my ODEs that the time is equal to infinity. As of right now, it just doesn't deliver a time. It's kind of an insidious problem and caused me to end up duplicating the ODE function for the steady state case, just because the steady state was actually a time equals 0. Okay, so on the positive side, it turned out that the function I was optimizing was pretty shallow with lots of local minimums. So it was better to actually examine 128 different ranges of parameters and sort of pick the best ones and average between those, kind of a more statistical point of view. And boy, I was really grateful that I didn't have to pay license fees for high performance computing. Additionally, MPI with SciML just works out of the box amazingly without really having to do anything. I'm not sure how it does that, but it's fantastic. The weird thing is that when you're in VS Code, I can't really get it to launch multiple threads, even though the settings are correct. So some recommendations moving forward. First off, I would say the documentation really should eliminate global variables. Like, let's set people up to write performant code from the start. Granted, it's going to make the barrier to entrance a little bit higher, but I think if it's explained clearly, that in the end, people will benefit. Again, it's this benefit, ease of use of the scripting language versus having performant code. Now, if you eliminate global variables, you're going to have lots of closures, and that entails its own cost. Additionally, I've heard that OptimJL, the recommendation is to move to NLOpt, but to be honest, OptimJL is really robust. I don't know why, but it is, and I haven't had as much luck with NLOpt, to be honest. Although the SLSQP is pretty darn good and a good substitute for BFGS. Finally, there's an issue with early termination with steady state problems, and it has to do with the way that the absolute and relative tolerances are interpreted. And I raised these issues, and there was some feedback, but I don't know that a satisfactory solution was arrived at. These steady state problems, they terminate early, like really far from steady state. And I had to use some tricks to avoid that, which basically involved setting the tolerances extremely low so that they're never met, and then setting up essentially a Tmax. Even more curious is that with these steady state problems in the early termination, as well as with forward diff versus finite diff, I found that running the same scripts, you get different results on Intel chips versus AMD chips. And that's important. I don't know if that's just the nature of the chips or if there's something that's causing it, but it's a major issue, and I think one that really should be addressed. Moving forward, it causes problems. I wrote my code, solved it, on an Intel system, an AMD system and had my results, and they were different. And that was confusing, and took a while to track down that issue. You know, that's if you're doing simulations and you're getting different answers based on the machine, that's an important thing to know about. Finally, I'd like to end just by acknowledging people who've done the work, and thank you for your attention.
I think based on some of the issues raised, it's a pity that Don isn't here, because I found that with issues that had been brought into the discussion, there's quite a lot of, oh, we have solved this and this is how you can do it. So instead of questions, I think I'll open it up to the room for comments. Maybe somebody has, yeah, I'd hope for that.
Yeah, most of those have pretty obvious solutions, right? So, I mean, so one of the big things there was if you have a chaotic model and you're running it on a system that is AVX 512 versus AVX 256, right? Like the issue is that larger SIMD vectors will cause different outputs in floating point calculations, right? This is just a property of SIMD. And so if you do want full, complete, absolutely the same floating point numbers between two different chips, you have to make sure that you either have AVX 512 in both cases, or you don't do AVX 512, or no SIMD, right? You know, this is just a property, like SIMD will change the floating point values. That's just like a baseline thing. And so you could test this on like Lorentz equation. You can find out what you can, if you solve Lorentz equation with an ODE solver, you can know what SIMD size vectors someone has enabled on their Julia compilation by the output of the Lorentz equation at time 100, right? So I want to write a blog post on that. So that's the last piece, right? The second to last piece, there's a new operation, steady state condition interface. This was just added probably 2 months ago. So this was done by Avik Paul for the deep equilibrium model stuff. I'm not sure it's well documented yet because it is quite brand new, but it does handle that whole case. So yeah, if anyone wants to help at the hackathon with documenting the new terminating conditions, that is the case. Before it was just doing a straight check of the whether the derivative is small enough, but now it has things like checking the history and options for all this kind of stuff. I think those were most of them that came to mind. That model would definitely improve for modeling toolkit, but that's a separate thing. You should not be doing main functions at all. That's a bad style, but that's a deeper discussion.
Yeah, and well, another solution that I found works with global variables, if you just type your globals, that, correct me if I'm wrong, that takes away the penalty of the type instability in the execution of your not main functions, but of your code. So that's how I found it. But used to constant them, but if you just type your globals, that works as well. And that takes away that penalty. Any other comments? No? Then, yeah, this is the end of the second session. We have another session after the lunch break, so come back. We have 4 more talks on this mini symposium, so see you all at 2 o'clock.